All right, so we're going to start our introduction to trigonometry today. Well, what is trigonometry? Tells you it's the branch of mathematics dealing with the relations of the sides and angles of triangles and with the relevant functions of any angles. So it does, the reason we introduce it here in the geometry section, because it does relate to triangles. Now I will tell you, we are going to get really just an introduction to trigonometry. We're going to learn the ratios associated. We're going to learn a little bit of calculator work, but we are really only going to be working on the a little bit of it. As you move on to later levels of math, you will learn more trigonometry. But I will tell you, when we get into this, this is very calculator heavy. And I will show you how we use the calculator when we eventually get to that part. Today we're dealing with ratios, which is just dividing. That's all. Any calculator can do this. There's nothing special what we're going to be doing today. Today is all going to be about ratios, which is just dividing two numbers. Okay. So task A says, sketch a line segment parallel to segment BC, intersecting triangle ABC twice. Label the intersection point on the hypotenuse as D and label the intersection point on the leg as point E. Now I am going to shrink this down just a tad to give me a little bit more room here on the page. So what that means, I'm going to take my straight edge. You can draw this line wherever you want as long as it's parallel to BC. I'm just going to use my ruler and draw my edge there. Now, there is a very good chance we did not draw that in the same spot, and you don't have to draw it exactly where I draw it. It does have to be parallel. That is the only criteria, that you do have to draw that segment parallel. And because they're parallel, that means our right angle is going to stay here. And we can put the markings to show that those two lines are parallel. It said label the point on the hypotenuse as D. So up here is going to be labeled point D, and the other one as point E. Again, as long as your segment is parallel to BC, it doesn't have to be drawn in the exact same spot as me, because we're going to show that through the ratios it will all work out. Now, question 2 says, is triangle ABC, and there should be a similar, that tilde should be in there between the two triangles. Is triangle ABC similar to triangle ADE? And the answer is going to be yes. I'm not going to get into a long explanation of why, because we did not do the proving part of similar triangles. We just talked about what are similar triangles. And there is a theorem called the angle-angle similarity theorem that says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. Well, since that 45, that angle A is in both the smaller triangle and the larger triangle, and they both have right angles, it does fit the definition of similar triangles. Now, just to remind ourselves, what does it mean for the two items to be similar? Which is why we did that unit before we did this. It does mean all corresponding angles are congruent. Bless you. and all corresponding sides are proportional. And again, that's just a reminder of what is the definition of similar figures. Now it says, using your ruler, record the side lengths of triangle ABC and triangle ADE in centimeters. Now, we should have the same measures for triangle ABC because we all have the same one drawn on a piece of paper. Our measurements for triangle ADE might not be the same because of where you drew your line. So the segments that we need to measure, we need to find out what does AC equal, what does BC equal, and what does AB equal. Those are the three sides of the large triangle. And then we need to do the same thing for the smaller ones. So AE, what does it measure? DE and AD. So I'm going to pause for a moment while you go ahead and make sure you're measuring in centimeters and measure all 6 of those parts and record your measurements, and then we'll come around and talk about them. We should agree on triangle ABC or be very close. Triangle ABC, we could be off by like 1/10 of a centimeter because, again, I've talked about this. We are human. Anytime humans get involved, there is always that chance for error because if we don't line up that ruler exactly, it could be a little off. But we all have for the bigger triangle, we all have the same triangle drawn on the paper, okay? So that one we should be closer. The second one, it depends on what you drew. Your numbers should not match my numbers on the second one, okay? So what did we get for AC? How long in centimeters did we say that segment AC was? 9.3. So again, could be a little off there. A 9.2. Some, if you're in that ballpark, you're okay. What did we get for BC? 9.2. So again, we're in that ballpark. And what about AB? Everybody got 13? I had gotten 13.1, so again, that would be in the ballpark. Now again, the second set of numbers I can't get from you because it depends on how you drew that segment. For me, my measurements, AE is 6.9 centimeters, my DE was 7 centimeters, and my AD was 9.9 centimeters. Again, those should not be your measures because your drawing on your book is different than what I have on mine. You should be going with your measurements that you were supposed to do. Now, it says we know that right triangles consist of 2 legs and a hypotenuse. When we studied the 30, 60, 90 triangles, we learned that the short leg was opposite the 30-degree angle and the long leg was opposite the 60-degree angle. In trigonometry, the legs of the right triangle are referred to as the opposite leg and adjacent leg. To determine if a leg is the opposite or adjacent depends on the angle you are looking at, called the reference angle. The opposite leg is the leg opposite of the reference angle. The adjacent leg is the leg adjacent to the reference angle. So given triangle ABC, identify the opposite leg, adjacent leg, and hypotenuse using angle A as the reference angle. So I come back here, they're saying, hey, I want to use this angle here. Here's angle A down in the bottom. They're saying This is my reference angle. So basically they're saying if I'm standing at angle A, how would I identify opposite leg, adjacent leg, and hypotenuse? Now, hypotenuse has not changed. Hypotenuse is always opposite what? The 90-degree angle, the right angle. So the hypotenuse, no matter what triangle we're talking about, is opposite that 90-degree angle. So this side over here, either segment AD or segment AB, is going to be our hypotenuse. That is always opposite the right angle. Now we have to talk about which one is the opposite leg and which one is the adjacent leg. So if this is my angle, my reference angle, opposite, I'm going to draw two lines because I have two opposite sides here. Opposite of that angle are BC and DE. So these would be considered opposite legs. Because they are across from or opposite from that reference angle, which means that AE and AC would be the adjacent legs. And again, this only happens because angle A is our reference angle. If we changed our reference angle to angle B, opposite and adjacent are going to end up switching. And that's going to be very important to understand as we get deeper into this unit. But we have to know what is our reference angle? Where are we looking from? Because it changes depending on our viewpoint. Hypotenuse does not. It is the one that does not change based on our viewpoint. The other two depend on where are we standing as far as opposite goes and adjacent goes. All right, so now on the next page, they want us to take these measures that we just found. It says using angle A as the reference angle, determine each side length ratio. Write your answer as a fraction and as a decimal rounded to the thousandth. The thousandth is 3 decimal places. So the leg opposite of angle A, we said was segment BC. The hypotenuse, segment AB. For the smaller triangle, the leg opposite became segment DE, and its hypotenuse is AD. We go down to leg adjacent. For the larger triangle, that is AC. The hypotenuse is still AB. For the smaller triangle, AE over AD. And then opposite and adjacent, we already found opposite and adjacent here. So that's going to become BC over AC. And DE over AE. So now we need to fill in those measurements. What did we say was the measure of BC? I'm going to scroll up for a moment. We said BC was 9.2. And AC was 13. If I take 9.2 and divide it by 13, I get 0.0 About 0.708. If I take DE over AD, now again, this is your measurement, so this second column is whatever your measurements are. For me, DE was 7 over 9.9. Which gets me 0.707. Are those two numbers very close together? 0.708 and yeah. Again, there's probably a little human error involved in the measuring there. AC over AB. AC we said was 9.3. Over 13. This is 0.715. And then again, I'm going to use my AE over my AD. And that comes out to 0.700 for me. Again, yours could be slightly different. And then if we take BC 9.2 divided by 9.3, we get 0.989. And if I take my 7 divided by my 6.9, I get 1.014. Again, even though those numbers aren't looking the same, they are very close, and there's a little bit of human error involved. But if you look at that last row, 0.989 and 1.014, those are both very, very close to being equal to 1, which they should be because, again, they gave us a 45, 45, 90 triangle on the first one. And we know that the legs of a 45, 45, 90 triangle are congruent. So how does the table confirm what we already know? The table confirms that the legs of a 45, 45, 90 triangle are congruent. And again, I know the ratios are slightly off, but the bottom row are both very close to being a ratio of 1 because those sides should be equal to each other, being a 45, 45, 90. Again, tells me I have a little bit of human error in how I measured my own triangle and how we measured the triangle that was on the page. We could be slightly off there. But again, it still confirms what we know, that the legs of a 45, 45, 90 triangle are equal to each other. All right, now in number 7, it says sketch 3 segments, segment DE, segment FG, and segment JK, all parallel to AC with endpoints on triangle ABC. So again, now we're going to take our straight edge, but we're going to run it parallel to segment AC. And I'm going to draw in, again, there's no way for you to draw yours exactly as I draw mine. I'm just drawing in 3 separate segments. And again, it said to draw in 3 parallel, which tells me that all 4 of these lines here are parallel. And if one of them has a right angle, that means those right angles. It's creating 3 new right triangles inside of the original right triangle. And again, one of the segments is DE, one of them is FG, and one of them is JK. And with all of these new triangles, angle B is 60 degrees. We have 90 degrees all the way down, which means all of these angles on the left side are all going to be 30 degrees because, again, that's the only way each triangle would add up to 180 degrees. So we have 4 30, 60, 90 triangles here. Now, on the next page, it's going to have us do more measure, but it says this time, using angle B as the reference angle, determine each side length ratio. Write your answer as a fraction and as a decimal rounded to the thousandth. So again, this time we're changing. Our reference angle is up here, okay? Angle B is now our reference angle. And again, hypotenuse does not change. The hypotenuse is opposite the right angle. So this side, and I'm writing it out kind of far because I'm going to have to do all those measures. So I'm leaving myself room to measure each of those. So I'm saying that side is the hypotenuse. But now we have to do the opposite and the adjacent. So looking at the large triangle, segment AC. Would that be opposite of angle B or adjacent to angle B? Would segment AC be opposite of angle B or adjacent to angle B? Angle B is up here and AC is down here. Yeah, so this side is going to represent all of these segments here. I'm not going to write it on each one, but all of these segments here that are parallel, these are all going to represent the opposite leg, which means that all of these segments down on BC, these are all going to represent the adjacent leg. And again, I'm writing these titles out a ways because now we have to go in and measure all the sides of all 4 triangles. So when I measure the large triangle, because the large triangle is the only one we should agree on because, again, it's the one triangle we all have written on our paper the same. So when I do the hypotenuse AB here, I get 12.4 centimeters. When I measured AC, I got 10.7 centimeters. And when I measured BC, I got 6.4 centimeters. Now you need to go in and measure each of your smaller triangles. You need DE, FG, JK, DB, FB, JB, BE, BG, BK. So I'm going to pause while you go in and get your measurements. Again, they will not be the same as mine. So you need to go through in centimeters and measure all those different segments on your paper. Now again, I added in all the measures from how I drew those triangles, those numbers, except for triangle ABC. Those other numbers we probably do not match up with, and that's okay, though we're writing ratios with them. But that's all the measures that you should have. You should have all 3 sides of all four triangles. Now what they want us to do on the next page is like we did previously, they want us to write the ratios, and they have all four triangles represented here. So what they want, first they want the leg opposite angle B over the hypotenuse. So for the larger triangle, that would be AC over AB. Then for triangle DBE, that would be DE over DB. For triangle FBG, that would be FG over FB. And for triangle JBK, that would be JK over JB. So in just a moment, those are the ratios you're going to fill in your numbers for and calculate their values. For the leg adjacent to angle B over the hypotenuse, for the first one, that would be BC over AB. Then triangle DBE would be BE over DB. Triangle FBG, that would be BG over FB. And for triangle JKB, that would be BK over JB. And then that last row is just taking the numerators from the first two and putting them. So here I have AC over BC, DE over BE, FG over BG, and JK over BK. So now I'm going to pause for you to fill in those ratios from your measurements on the previous page. And again, then take those ratios and turn them into a decimal with 3 decimal places. So again, the first column, triangle ABC, we should agree on these ratios because, again, we all had the exact same triangle here. So for AC, we should have 10.7 over 12.4. And when I take 10.7 and divide it by 12.4, I get 0.863. And then if I do BC over AB, that is 6.4 over 12.4, which comes out to 0.516. And then if we take the 10.7 over the 6.4, we get 1.67. Again, that column, we should all have the exact same numbers because that's about triangle ABC that was on our paper. Now for the triangles we drew, I'm going to use my numbers. For DE, I had 7.8, and for DB, I had 9. And if I take 7.8 and I divide it by 9, I get 0.867. And then if I take my BE, that's 4.4 over 9. I get 0.489. And then if I take the 7.8 divided by the 4.4, I get 1.77. do the same thing now for triangle FGB, or FBG, excuse me. This would be 6.1 over 7.1. Again, these are my measurements based on my triangle, which gives me 0.859. And then I have 3.4 over 7.1. Is 0.479. And then 6.1 over 3.4 is 1.79. And then for my last triangle, I would have 4.9 over I have a bad measurement because I can't have my leg be longer than my hypotenuse. Let me double check my measurement here because I have JK at 4.9. And then JB should be 5.7. I have a wrong measurement there. Let me correct that. And I knew it was wrong because remember my hypotenuse has to be the longest side of a right triangle. So that last ratio I have 4.9 over 5.7. And when I take 4.9 and I divide it by 5.7, I get 0.860. And then I have 2.7 over 5.7 for the next one, which gives me 0.474. And then if I take 4.9 and divide it by 2.7 as my last ratio, I get 1.815. Now again, there is some human error involved here. Wait, not. Are all these ratios the same? No, but if you look across a row, 0.863, 0.867, 0.859, and 0.860 are all very, very close to each other. Again, there's some human error. All right, so now that we've got all these ratios in for the 4 different triangles we created, now it's asking us, how does this table confirm what we already know about 30, 60, 90 triangles? Well, the 2 things we know about 30, 60, 90 triangles, we know that the hypotenuse is equal to 2 times the shorter leg, and the longer leg equals the shorter leg times radical 3. Those are 2 relationships we already know. So how does this chart confirm that? Well, if we go back, I'm going to scroll back up just for a moment here to the triangle we were working on. Remember, we had our 30, 60, 90 triangles. We created 3 more triangles within the big triangle. And we yesterday talked about opposite leg and adjacent leg from the reference angle. But we also, with 30, 60, 90, we have other names for those. Based on B being the reference angle and that being 60 degrees, that opposite leg would also be known as our longer leg. Which means the adjacent leg would be known as our shorter leg because the hypotenuse does not change. So because we are using a 30, 60, 90 triangle here, to showcase these relationships we were doing, we also have to look at that adjacent is the shorter leg, opposite is the longer leg. So when I go back and look at some of these relationships, where I want the hypotenuse is 2 times the shorter leg, if I'm going to just use that first column, that triangle ABC where we all had the same triangle. If I use that and say my hypotenuse was 12.4 and my leg adjacent in this case is my shorter leg, would be the 6.4. Now again, if I didn't measure exactly correct, these numbers could be slightly off. So if we said our hypotenuse was 12.4 and then 2 times our shorter leg of 6.4, we get 12.4 equals 12.8. Now, I know those two numbers are not exactly equal, but are they very close to each other? Had I measured super accurately, those numbers probably are closer and they should be equal. So it does show that that shorter leg is double the hypotenuse. And again, the longer leg is my opposite leg, which is my 10.7 equals my shorter leg of 6.4 times radical 3. And if I use my 10.7, or sorry, if I take 6.4 times radical 3, so I had 10.7 here, 11.1 here. Again, they're not perfect, but that comes down to me not being perfect. Are they really close? Does it show that that longer leg is a shorter leg times radical 3? Even though, again, the numbers don't come out perfectly equal, it does come pretty darn close, taking into account that there could be some human error going on in there. So it does show, even with the ratios we're looking at, that those special right triangle relationships, we saw it in the 45, 45, 90 in the previous chart, where that relationship did exist. The legs were equal to each other. So this table, as we're getting into these trig ratios, shows that relationship between the trig ratios and those special right triangles. And I believe that was one of our essential questions, talked about how do they relate. And I showed you basically the special right triangles are just shortcuts of these relationships. And this table is showing you that this relationship does exist.